work energy theorem. It's a theorem that states that the total work done by all forces acting on an object is equal to the change in the kinetic energy. So what does that mean? Since we know that work is equal to the force multiplied by the distance, so when a force is applied to an object, this will create a displacement, a change in the position of the object. And this change in the position is related to the kinetic energy, which is also related to the motion. Okay, so a force does work on an object, and so the kinetic energy of that object will either increase due to the force or it will decrease due to that force. So the increasing and the decreasing of the kinetic energy, since we're talking about the same object, so same mass, should be related to what exactly? It should be then related to the velocity of that object. Okay, so I'm going to show you how we can state the formula. So let me just remove all of these. Okay, so we know that work, if I want to just state what I just said, is half mass velocity squared, final velocity squared, minus half mass velocity initial squared. Okay, so we can develop that furthermore in saying the force multiplied by the distance, that's the work, is equal to, since we're dealing with the same mass, it's half mass, so we can take those together and then get VF and VI into bracket, and so we will get what? Force multiplied by distance is half mass times the change in the velocity. That's because, once again, if I want to express this formula by using phrases, we can say that, okay, we can say that a force, this is the force, it does work on a block, let's say. So the kinetic energy of the block will either increase or decrease, but since the block has the same mass, so the energy then should be related to the second factor, which is the change in the velocity. Okay, so either you will increase the speed or you will decrease the speed. By increasing it, you're increasing also the kinetic energy. By decreasing it, or let's say if you're applying brake to an object, friction, then this shall decrease. And all of this is related to how much distance this object will cross because of this force applied, and because of how much energy originally the object had. Okay, so it became really messy. Let's just take an example now. Okay, we have a car of mass 800 kg and it's traveling at 20 meters per second. Brakes are applied to it and it comes to rest, there's a T missing here, in 12 meters. They want us to find the average force exerted by the brakes. Okay, so let's take everything we have and let's first state the theorem that we know. Work is equal to the change in the kinetic energy. So force multiplied by distance is equal to half mass bracket, since again we're dealing with the same mass. Okay, so there's no need to write the complex one. Final velocity squared, do not forget the squared, minus initial velocity squared. Okay, so let's see what we have already here and what we don't have. We have the mass, okay, we have one velocity, we will decide which one is that, is it VF or VI, and we have the distance that it crossed, and then there's this small keyword that is extremely important at rest. So it's because of the force that we want to get that is unknown, and after crossing 12 meters, The velocity of the mass 800 was 20 meter per second, and it comes to rest. So when I say it comes to rest, means that it became 0 meter per second. And so I can say that the distance is given, the mass is given, this is the initial velocity, 20, and the final velocity is 0. So let's put everything, substitute in the formula. Force is the one that we want to get. Distance is 12 half times 800 times 0 squared minus 20 squared. Okay, and then by completing the calculation, we'll have force times 12 equals to 400 times, or let's me, okay, do this, it will be minus, okay, keep that, I'll tell you later why. Now let's divide this by 12 and this by 12 to get rid of this from this side. And so we will get force is what? It's minus 1,333. I have 1, 2, 3, 4, 3 Newton. So this is the force applied by the brakes. Okay, and why is the force applied by the brakes a negative force? Why did it give me a negative force? Does this mean that it's strong? No, it doesn't, of course not. But since brakes are applying a force that is in the opposite direction of the motion of the car, since the car is moving forward, and the brakes shall apply a force that is opposite to this one, so the magnitude is 13,333, but the negative sign just shows the direction of that force applied. It just shows that it's being applied in the opposite direction. Okay, and this is a neat calculation. Example 2, we have a forward force of 9 Newton is applied to a load cart over a distance of 4 meters. If the cart, which is initially at rest, has a final speed of 6 meters per second, what is the mass of the loaded cart? So once again, we can apply the theorem. Okay, we can say what? We can say that work is equal to the change in the kinetic energy. So force times distance is half mass velocity final squared minus velocity initial squared. The subject here is the mass. This is what we need. This is what we want to get. It's 9.4. 9 times 4 is equal to half mass velocity squared. It was initially at rest. So in this case, VI is the 0 and VF is the 6 meters per second. Just pay attention to that. And so substituting everything, we will have this relationship. 36 is equal half mass 36. So mass is equal to 2 kg. So the cart is loaded with 2 kilogram stuff. Third example, a 24 kg boy slides down a slide that is 6 meters long, initially at rest. So once again, we have the keyword at rest, which means 0, initially at rest. So VI is equal to 0 meters per second. And the boy's speed at the bottom of the slide was 2 meters per second. So that's VF of the boy. Don't forget that we need to square this. What is the magnitude of the net force acting on the boy? So this is applying the theorem. It's the same thing. We just get the force. Example 4 is about Robin Hood, who is exerting an average force of 100 Newton in pulling back his bow by 0.5 meters. He fires the arrow of mass 2 kg vertically upward. Okay, so how much energy is stored in his bow? So we need to get the stored energy. Stored energy is the kinetic energy. It's the elastic, it's the strain energy here. Applying the rule, energy stored is equal to the work done. So how much work means how much energy is stored. So you just multiply the force that Robin Hood applied and by how much it was stretched out by, so the distance, so force multiplied by distance, you'll get what? You'll get 50 joules. This is how much energy was elastically stored in his bow. Now, how high does the arrow go? This energy that is elastic should entirely be converted to GPE, as all the energy is conserved. So we can say that since the energy is conserved, then the elastic energy must be equal to the kinetic energy and equal to the potential energy as its highest point. Since energy is equal to the mgh, and so h is equal to E divided by mg, so it's 25 meter. Okay, so as you can see, the work energy theorem, it can be applied using the change in the kinetic energy, or sometimes by just applying the formula itself, like by getting the work done and say, oh, that is the energy or whatever type of energy we have, because here we have we have strain potential energy. Okay, so sometimes it's simple, like this example, really simple, and sometimes it's harder, where you have to state the formula, the theorem related to KE specifically, and solve the question to get the variable needed. Okay, so sometimes it's simpler than we think it is. Last question is, why would the actual height be slightly less than the one we have calculated? For sure, that's because we have friction force, as the arrow is being lifted up to the highest point. So the GPE, theoretically, we consider that it's entirely converted to GPE, but this will for sure be slightly less due to the friction force. While it's being raised up, we will have friction applied to it, so it will be lost due to heat and maybe sound as well. Okay, so the GPE will be slightly less.